Good morning, good evening, good afternoon, and good night. My name is Jeremy Anthony Gunawan. I am from Numerical Method 1, and today I'm going to show you the assistant assignment given by our assistant, Miss Faiza. So, the first week, our Numerical Method assistant, Miss Faiza, told us to do this assignment, which is to do a few variations on the velocity of CFD soft using gate valve. So we have done this before, but we only use one velocity. So this time we will try uh, three new variations, which is 0.7 meter per second, 1.2 meters per second, and 1.5. So these are the instructions that are needed to do this assignment. So the first time we import the geometry file, which is the gate valve itself, and then we use the uniform scaling to make sure that the three axis fits, and this is the dimension that we get. We aim to measure the dimension as it is. The next is we make the mesh of the model, and by putting surface environment maximum level 2 and the layer mesh parameters, the 5 number of layers. Expansion ratio is 1.25, and the first layer of thickness is 0.2. And don't forget to set the box mesh boundaries. The x negative is inlet, and the x positive is outlet. The y positive is wall, and the others are boundary. So before generating the mesh, we have to place the mesh location inside the valve, right inside and in the middle of the valve. This is the coordinate I got. You may get different coordinates according to your own geometry. Now, the next thing I did was I generated the mesh, and it shows that the mesh is okay. So we can continue. The next is simulating the model, but before that we have to set up a few setups first. Like we change the turbulence here from laminar to RANS, RANS, and then it'll pop up a new tab called turbulence, and then we set the turbulence model to SST K omega, and then they change the material to air. Next, we can set the inlet boundary conditions, and the reference value velocity is the one that we're going to change every time. So let's start up with 1, and then we'll change as we go on. And then we'll check the outlet, make sure it's outflow. We check the inlet, make sure it's velocity inlet, and the wall is stationary wall. After all the preparations are done, we can start the modeling, the simulation model. We can set the iterations to 1000, and then we'll run the simulation, also in the interval. So after that's done, we go to another software, which is PetaView, and we put in 4 formulas, which is P static, which is static pressure. This is the magnitude of the speed, the velocity, dynamic pressure, and the total pressure. So after we input these formulas according to each of their own formula, we can get these data, which is the inlet and the outlet, the total pressure and the total outlet pressure and the total inlet pressure. After finding the pressure, we can find the fluid discharge with these formula. Q equals to A times V, which is A area of inlet times velocity. And these are the data that I tried. So the first time we've done the 1 meter per second velocity. Now after trying 3 different velocity, which is 0.7, we can get these data. Same goes with the 1.2 and the 1.5. So from the data, I made a graph that shows that velocity over the pressure drop. So we can simplify that these graphs are directionally proportional to the pressure drop. So the higher the velocity and the higher the pressure drop, and vice versa. Thank you for listening. Goodbye.